Today we are going to see one of the advanced control for grid forming inverter, that is Deadbeat predictive voltage control. So this is the schematic for MATLAB Simulink. So for the inverter, we have the DC voltage source at the input, and at the output we have measurement block, and then this is the LC filter, and at the output of LC filter, again this is the measurement block. From here we are getting these variables for the voltage and current, and after that there are two loads connected. The first load is always connected of 4 kilowatt and 1 kVr. Then a three-phase circuit breaker is connected to switch on the load 2 at time equal to 3 seconds, and that again turned off at time equal to 3.5 seconds. So let us see first how this Deadbeat predictive voltage control works for this three-phase inverter. So from this subsystem, we will get the reference voltage, and that is coming from the Deadbeat predictive voltage control equations, and that voltage gets passed through hysteresis band to generate the switching pulses. So for this Deadbeat predictive voltage control, we require these sensor signals, V out ABC, I out ABC, and I inverter ABC, and also we require LC parameter values, and also we require the reference voltage which we want to set at the PCC point. So if you go inside, these are the controller equations for phase A, phase B, phase C, and this bottom one in the reference voltage generation at the K plus 1 instant. So we will see later how we have implemented this equation for phase A, phase B, phase C. And let us, if you go inside this reference voltage generation, so this is the phase A, phase B, phase C, and we have implemented these equations through these blocks. Simply you just uh, pause over here and you see how this equation is implemented in the blocks. And we have also checked the performance of controller by changing the reference RMS voltage from 120 volt to 230 volt by using these blocks. So at the time t equal to 2 seconds, our reference for the voltage gets changed from 120 volt to 230 volt, and we will see how this controller performs if you change the reference voltage from arbitrary values like from 120 volt to 230 volt. So this is the schematic for this voltage generations from this Deadbeat predictive controller, and then this estimated voltage, it gets passed through the hysteresis band to get the switching pulses. So you can see over here how the switching pulses gets generated. So let us run this simulation. So initially we have set the voltage reference 120 volt. So in this display block, you can see that our controller able to track, and this RMS voltage is coming as 120 volt. And at time t equal to 2 second, our reference gets changed, and it is able to track to 30 volt. Now let us see the waveform of voltage and current. So this top one is the voltage we are getting at the output of converter, and this bottom one is the current waveforms. So at time t equal to 2 second, we have changed the reference. So you can see it is able to track the reference voltage very smoothly and very fast. And at time equal to 3 second, our load gets doubled. So you can see there is no significant variation. There is no variation in the output voltage waveform, and there is no disturbances, you can say, in the output voltage waveform, and only this current gets double. So this means that our controller is working perfectly for this Deadbeat predictive voltage controller. And you can see also the startup of converter. This converter starts very smoothly, and it is able to just from the voltage at time equal to 0.05 second. So from this waveform you can see that our controller performs well. So for this implementing this Deadbeat voltage controller, let us see how we have implemented. So if you so what is deadbeat controller? So in general, the deadbeat controller is discrete time output feedback controller in which the penalty on control is assumed to be zero. And for if you apply this deadbeat controller for the voltage control, so that maintains constant voltage at PCC, and it offers fast and accurate tracking of the reference voltage. So this is the block diagram for deadbeat predictive voltage control for the grid forming inverter. So we require these sensor signals, and we also require filter parameter values and the reference voltage, and then it finally provides this UCK star for this to get passed through hysteresis band to generate the switching pulses. So let us see how this controller works. So for that we require this filter dynamics. So we have LC filter at the output converter, and we can write this state space equation for the capacitor inductor dynamics. So the state variables are voltage across the filter capacitor and current through inductor. So if you apply KVL and KCL, you get this equation number 1, and then you get equation number 2, and then you can get easily this state space equation. And now we will need to convert this state space equation into discrete domain for sampling state of k. So you will get this equation, and we can find this relation for this output capacitor voltage at the k plus 1th instant, and this is represented by equation number 3. And we need to design the deadbeat controller for the reference voltage of VT start to 30 volt per phase at 50 hertz. So for that we need to consider the flowing cost function that is multiplied by 4. So this cost function needs to minimize by differentiating with respect to issue k and equating to 0. So on substituting fifth equation to 3, you will get finally this expression, and in the simulation we have implemented this equation only, that is equation number 6. So in the simulation, if you see, this equation has been implemented. So here you can see phase A, phase B, phase C. This equation is nothing but this one equation, this equation number 6. So ECK star is maintained around hysteresis band to generate the switching pulses for the grid forming inverter. So from the subsystem, you will get this UC star K. For the subsystem, you will get UC star K, and this UC star K is going through this hysteresis band to get the finally switching pulses. And 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 after that, for implementing this equation, we need to calculate all these variables in the matrices G11, G12, H12, and H11. So we need to calculate all these variables for this state matrix and input matrix. And for that, we have to find this in state matrix and input matrix. A state matrix is nothing but a state transition matrix, and you can find H matrix also by using this equation, and by substituting the LC parameter values. So we have LC parameter values given over here. So you will get all these variables, and finally we'll get all the variables in the matrix. So on substituting this all variables in the state equation, you will get this equation, and you can easily implement the Deadbeat voltage controller equation. And we have also set this reference voltage at k plus 1th instant. So we have used this equation for getting the reference voltages, and these are references for the Deadbeat voltage controller for the grid forming inverter. So this is the schematic for the MATLAB Simulink, and this is the script for all the variables that we are using for the simulation. So we have sampling time 2 microsecond, and this angular frequency, and this phase lead for next sample reference voltage phi, that is 120 degree in radian. Hysteresis band is 0.5. LC parameter values given over here, and all the variables that we have computed from this Deadbeat predictive voltage control equation are written over here. I will provide all this variable data in the description box. That's all. Thank you.